What's that sound? It's For Amusement Only, the EM and Bingo Pinball Podcast.
Welcome back to For Amusement Only. This is Nick Baldridge. After last night's podcast, I did some reflecting and thought, why don't I take a step even further back and talk about the basics of electricity and electrical theory. I've realized, based on some of the questions that I receive privately via email and so forth, that some folks out there might not have as thorough an understanding as I feel the subject warrants. So you get to suffer through me talking about Ohm's Law. Get ready. So the thing to remember about electricity is that it always wants to flow. The electrons want to travel, and they just need a path to do it. All the switches in a pinball machine are set up to allow that electricity to flow when switches are closed. When they're open, it prevents the electricity from moving. If you take a big step back from pinball machines and think about electricity in its basic form, let's say you have a battery. A battery has a negative side and a positive side. If you were to wire a jumper between the negative side and the positive side of the battery, over time the battery would likely overheat, because batteries, like AA's, for example, are not made to charge themselves, and that's what's happening. But if you take that battery and you take a bit of wire and you put a light bulb in between the positive and negative side, then the current's going to flow. In this case, the electrons are actually going to move from the negative to the positive side of the battery, and it goes through the lamp, which offers a resistance. The battery itself is what's completing the circuit. It's what's providing the power, and it's what's allowing the electrons to flow. If you take the battery out, the lamp doesn't light. You take the lamp out, the battery doesn't light, unless you connect the ends of the jumper together, and then it will. So we've got a load. A load is anything that is applied to an electrical circuit that the circuit is actually powering. Now, this load you can think of as resistance, because anything that you put into an electrical circuit will act as a resistor does and impede the flow of current. This resistance can be given off as heat. It can be given off as kinetic energy, such as a motor. It can be given off in a variety of different ways, but it has to be given off in some way. So, let's talk about resistors. Resistors exist in a circuit to impede the flow of current, as I just said. But instead of being just a way to conceptualize it, that's actually all that they do. They're just a thing that sits in the circuit, and it impedes the current flow to allow for the load not to be overdriven. It prevents an inrush of current somewhere. Now, they exist in EM machines largely to allow for continued operation of the coil without setting it on fire. But they can also be used in high power switches to prevent arcing and the like, because again, it's impeding the flow of current. So if the current can't get there fast enough, it's not going to jump the gap. So next, let's talk about what happens when you put a resistor in the circuit. Aside from impeding the current flow, it's going to give off heat. Any resistor in a circuit is going to give off heat because it's an increased load in the circuit, and that load has to be dissipated in some way. Since it's not moving, hopefully, then it's got to be given off as heat. That's why if you see those big cement resistors or sand wound resistors and you touch them, either directly after their operation or while they're operating, which is not a great idea, but if you do, you'll see that they're burning hot. And that's the reason they're cement or sand wound instead of just the plain old teeny tiny wire wrapped ones. So, aside from resistors and resistance is measured in ohms. So if you have a multimeter and you see the omega symbol, that is the unit of measurement for resistance. If you take your meter and apply it across a resistor, it should read within tolerances the either the amount indicated that's stamped onto the cement resistor or the amount indicated by the colored bands on a typical tiny resistor. Those colored bands, depending on their position, determine the value. Now, each resistor, when I say within tolerances, can be plus or minus up to 10%. So we have current, we have resistance. We need one more thing in order for our circuit to work, and that is voltage. Voltage is actually electric potential. It's potentially what's going to happen when that circuit is active. Without the potential, you can't have current flow. Now, taking our simple circuit with a battery, typical AA battery provides 1.5 volts of potential. In order to determine the amount of current flow, you have to do a math problem. So I mentioned Ohm's law at the beginning of this podcast, and Ohm's law is critically important for determining any of the three components of a circuit. You have voltage, you have current flow, and you have resistance. Voltage equals current times resistance. Now, if you know 2 out of 3 of those variables, you can always solve for the third. And you do that by transposing that equation in any way that you need. Now, here's the very difficult thing about this. You can measure resistance with the machine off. You can measure voltage with the machine under load, but you cannot measure current while the circuit is complete. So I was mentioning how to use a meter yesterday in order to measure the values in your circuit, and you put one lead over here and you put the other lead over there. That's all well and good, but if you're trying to measure current flow, if you're trying to solve that mathematical equation to see if something is drawing too much current, you actually have to insert yourself into that circuit's path. So the current has to flow through your meter in order for the current reading to be accurate. That means that you have to desolder. Let's say you're trying to measure a coil, right? So you desolder one side of the coil, you put your meter, the black lead on the wire that you just desoldered, you put the red lead on the lug of the coil where that wire used to go, then you should get a pretty accurate reading on the current setting on the meter. Now, currents are measured in amperes, so that would be the A setting on your meter. Depending on how old your meter is, it might be the I setting. Also worth noting, voltage comes in 2 different types. You've got DC volts and you've got AC volts. My podcast yesterday about using a meter basically focused on AC, because that's what you find in most EM machines. In a newer machine from the early to mid 70s on, you're going to have DC circuits. And in some incredibly old machines, as I mentioned many episodes ago, that had their own rectifiers. So, it's crucially important to know if your circuit is AC or DC. You can find this out by reading the schematic. I've talked before about rectifiers, and if you have a wire that's coming off of the rectifier, that means it's been converted to DC, and anything in that circuit's path is going to be DC. If you have something coming directly off the transformer, on the other hand, that's going to be AC. So I've talked about the difference between AC and DC previously, but DC stands for direct current. That means that the amount of current that's flowing to that circuit is never going to vary as long as the resistance and the voltage remain the same. In AC, however, which stands for alternating current, in the US, it changes direction 60 times a second. So it switches from positive to negative and negative to positive and back again 60 times a second. In parts of Europe, it's 50 times a second. If you've ever wondered why in earlier times you couldn't take, say, a video game or a VHS tape and bring it to the US, that has to do with the number of times per second the electricity switches direction. That also informed the refresh rate of TVs, but we're getting rather far afield from pinball, so let's come back. 60 times a second in the US, the current is changing direction from a standard wall outlet. Because it's changing direction so quickly and so frequently, you have what looks like a sine wave generated from a pure AC source. So let's jump back to our really simple circuit. We got a battery, we got a jumper wire, or two jumper wires rather, and a light bulb in between. Now how do we turn this light bulb on and off? That's with the switch. Any kind of switch will do. However, we probably want it to be a toggle switch, so we can turn the lamp on and off at will without burning ourselves. This switch prevents current flow based on whether it's normally closed or normally open and how the switch is connected in the circuit. If the switch is normally closed, that means that you must interrupt the current path. If the switch is normally open, you need to close the switch in order for the current to flow. This probably raises more questions than it answers, and I tried to keep this relatively simple. In fact, I erased almost an entire podcast worth of material and re-recorded it because I thought it was getting a little too complex, and it still might be a little too complex. I will delve into this topic a bit more in future podcasts. I'll try not to overwhelm. Well, thank you again for joining me. My name again is Nick Baldridge. You can reach me at foramusementonlypodcast@gmail.com, or you can call us on the Bingos line at 724-BINGOS1. That's 724-246-4671. You can listen to us on iTunes, Stitcher, Pocket Casts, via RSS, on Facebook, on Twitter at Bingo Podcast. You can follow me on Instagram at nbaldridge, or you can listen to us on our website, which is foramusementonly.libsyn.com. Thank you again for listening, and I'll talk to you next time.